Today is the first day of the seminar, Seminar, and our first speaker is Frabat for the French, Francesco Battistoni, and
Italian champions of Bang, let's see, most important academic achievement.
And today he will give an introduction about elliptic curves.
Okay, thank you, Matteo. So today we start this tiny cycle of seminars about elliptic curves, and I wanted to start with a short introduction overview of why elliptic curves are important for several things in mathematics, like, for example, their role in geometry, their role in arithmetic, and if I have time, I would also like to say something about their role in cryptography, since they are really used right now in cryptography. I just said that Federico is not here because he was the one that organized everything, but I think he will be here for the next lessons. So, okay, let us start. And I think I want to start with just an introduction on the fact that this is, in some sense, a bad name for these objects. So part 0 of the seminar will be just explaining briefly why these are not ellipses. Because people who don't know what elliptic curves are, maybe they can think that elliptic curves are ellipses in some sense. The answer is no. So whenever we have a thing like that, this is not an elliptic curve. Okay, this is just a reminder, but I want to explain why German people and French people in the 19th century used this definition that unfortunately we carry on today. Because the idea, in fact, for this name was the following. Assume that you have a circle and you want to compute the length of this arc of the circle. How can you compute this? You know from the basic courses in analysis that, okay, if this is the curve, which is defined gamma t equal to xt, yt, and the relation is this one, classical relation, then you know that you can compute the length of the arc of circle you're interested in by just integrating this. You have to take the integral of the square root of square of the derivative of x with respect to t and square of the derivative of y with respect to t. And okay, now just do the computation. Compute here the derivatives. You substitute the terms in y with the terms in x using this relation. And then if you do the computation, you will arrive at this thing. Yes, which with a change of variables, just call z equal x of t, you will obtain this integral. Perfect. This is just change of variables. So the length of the arc of a circle, in fact, you just need to compute this integral. Now, from a basic analysis, you know what this integral is. It is the arc sine of z, which is, you know, the inverse function of a trigonometric function, the inverse function of sine of z. Okay, so this is the particular case whenever you are interested in the length of the arc of a circle. This length is given by the inverse of a trigonometric function. And in particular, you see here that the denominator, you can think of this as, let us call it u equal square root of 1 minus z squared, which again gives you exactly the equation of the unit circle. Now, suppose that you want to do the same thing, but instead of considering a circle, you consider a generic ellipsis. You can do exactly the same thing because, okay, you define your curve, the coordinates satisfy a relation like this with different coefficients, and you do the computations exactly like this. What is the problem now? The problem is that, again, you obtain an integral which in general would be of this form. Where you see now it is a bit more complicated because in general, instead of getting a quadratic, you obtain a cubic here where lambda is a real parameter.
So when you draw this arc, you mean the full thing, right?
Yeah, I'm taking for example, this arc of the ellipses.
Of the whole ellipse, you are just considering this part.
Yes, because yes, for symmetry, I just needed to consider on one part, especially because when I'm doing this integral, like here, I need to suppose that this is the graph of a function. So I just need to take a part. Okay, and when I do this, I arrive to this integral, which is now, in general, you cannot resolve this integral. You cannot resolve this by analytic formulas. But again, the idea is that there are two main ideas here. The first one is that exactly like here for the circle, the interesting object is not the integral, the arc sign, but its inverse function. So the idea is not to consider this integral, but to consider this the inverse of this. The inverse of this integral is called an elliptic function, which is called elliptic because you see it arises from this integral used for the computation of the arc of an ellipsis. This is the first idea, and here starts the theory of elliptic functions, which is widely studied. Elliptic functions satisfy some kind of periodicity, exactly like trigonometric functions with two parameters instead of one. And there are many things that we can say. But the second idea is connected to this, because here we said, okay, from here, from the denominator of the integral, I recover again the unit circle. What is the curve that I recover instead? From here, I take u equal to all these square root. I go to the squares. This goes to u square equal to this cubic polynomial. And here you can see exactly an example of what we call an elliptic curve. And this is the reason why they are called elliptic curves, because are the curves that arises from this elliptic integral. And yes, it's not a good definition, in my opinion, because these curves are much more important than ellipses in some sense, and I will explain why in the next minutes. But unfortunately, since most of the modern mathematics is now done using definitions that arose in the 19th century, with all the good things, but also the bad things that this means, then now we are kind of forced to call these things elliptic curves. and we will call them elliptic curves from now on. Okay, this was the historical introduction of about the name of these things, but now I want to explain really what elliptic curves are, at least from a geometric point of view. So I'm going to give a naive definition of an elliptic curve. For us, an elliptic curve will be a curve given by the solutions of this equation. So in general, for me, an elliptic curve, at least from a naive point of view, will be take the points in the plane, which are the solutions of y squared equal to f of x, where f is a cubic polynomial. So you see this is exactly an instance of elliptic curve, because here you have u squared and here you have a cubic polynomial. So, for example, if I want to draw two instances of elliptic curves, probably some of these graphs you have already made them in the past, in the sense that they are typical examples of nice curves to draw in the plane. I can take, for example, y squared equal to x cubed minus 3x plus 3. And if I draw this in the real plane, it will be something like that, where I have the symmetry, obviously, between the up and down, given by y squared. If I draw instead y squared equal to x cubed minus x, I draw this in the real plane, and I have again a similar thing, but drawn like this. Probably you have already seen this kind of drawings in the past, if you ever read something about elliptic curves. But as I told you before, this is in some sense a naive definition, because there are some things that I have to mention about this. Three things, actually. So, the first thing is that actually, when I talk about elliptic curves, I'm not really considering all the curves given by this equation, but I'm considering the non-singular ones. I want elliptic curves to be non-singular, which roughly speaking means that they have no singular points, so they have no singularities, no self-intersection points. And so, for example, if I take the curve given by the equation, y squared equal to x cubed plus x squared, it is very easy to see that the graph does something like that. And here in 0, I have exactly a singular point. You can see also, if you do the classical procedure by looking at the derivatives in x and y, you can see that the derivatives are 0 exactly when x and y are 0. So for us, this is not an elliptic curve, because this gives a singular point. Just like many curves in algebraic geometry, we want them to be non-singular. The second thing that I want to mention about the definition of elliptic curves is that, again, just like almost everything in algebraic geometry, actually, when I'm considering the curve, I need to consider the projective version of this curve. So I take again the curve that I drawn before, this one, x cubed minus x. Now I go to the projective version of this, and it becomes this cubic y squared z equal to x cubed minus x z squared. And why this is important? Because the thing now is that you can immediately see that in the projective plane, P2, this curve always has a solution, which is this point. And I mean, it is in particular a solution which is not related to the affine version of the curve, because you see here that I'm taking z equals 0. So this is a point, an infinity point, in fact, that is not described by this equation. So elliptic curves are in fact curves for which I can always choose an infinity point. And in fact, I can give an equivalent definition of elliptic curves by saying that they are projective curves with a specified base point. And the fact that we have this infinite point, which usually people call this O, it will be very important for why elliptic curves are so important, especially from a geometric algebraic point of view. And now the last thing I want to say about the naive definition of elliptic curves is that, okay, here actually until now
So, like by the previous thing, did you mean to say, like, if you take the affine version,
Mhm.
it may or may not have solution?
Yeah, exactly.
So, but the projective always has a solution.
Yes.
So this you get by homogenizing and dehomogenizing.
Mhm.
So any polynomial like this, if I'm not wrong, there's a one-to-one correspondence between like these two things, right? You can always homogenize and you can always dehomogenize.
Exactly.
So the solution is not preserved under this transformation.
Okay.
Depends on which line you cut. Like depends on how
I
you
mean,
cut them.
obviously, if I dehomogenize now with respect to y, I will see the solution now, because it will be the solution 0, 0 in this case.
But can you try to can you use this projective case to somehow get an idea of what a affine solution?
Uh,
No.
I think it depends. The fact is that usually the fact is that elliptic curves, you can define them also in another way, but if they are elliptic curves, they will always reduce to a thing like that via transformation, change of variables, and stuff like that. So in the end, you will always end with a situation like this. I think the main difference, this will become now also a question of the genus of the curves, because elliptic curves in some sense will be the only curves for which you always have granted that you have a rational point, a solution. In the sense that genus 0 curves, you can have that either they have no solutions or infinitely many. For higher genus, you have, for example, all the Faulting's results that they tell you that it's very rare to have rational points. And in fact, if you have them, they are finitely many, usually. Elliptic curves, in some sense, are the best thing because they give you all the wide spectrum of the number of solutions.
This one was a conjecture, right? He proved the last.
Yes, the last one was a conjecture. It proved in the 80s, I think, by Faulting's.
Okay, but so it's not the proof is not recent one, but it's
The elliptic curves case is the one that is
This
is way to die.
Okay, but that's different. Yes, to understand how many rational points, yes, it's conjectural for elliptic curves.
still a conjecture.
Yes. You have some subcases where this is solved, but in general, it's still conjectural. Yeah. Okay. So elliptic curves always have this infinity point, which will be important. And the last thing that I wanted to say is that, okay, until now, I was just implicitly considering elliptic curves to be solved over the real numbers. But now we know from algebraic geometry that when I study the equation defining a curve, I also have to consider which field are the solutions from. And for example, I take again this example of elliptic curve, and I want to give you three fields over which the elliptic curve will assume a different face. Okay, again, if I assume my solution to be two coordinate points with real coordinates, I have exactly the graph that I drawn here. But what if I take now the complex solutions? Again, I'm actually taking the solutions in the projective plane to be more precise. What I obtain, okay, first of all, let us remind that when I talk about a curve over the complex numbers, we can see them as surfaces over the real numbers because of the relation between R and C. So a curve is actually a two-dimensional surface. And the nice thing about elliptic curves is that as complex manifolds, elliptic curves are tori. And actually, you can do the vice versa in the sense that if you take any complex torus with a complex structure, you can always show that it is biolomorphic to an elliptic curve. You can always show that it is defined by an equation like this. And then, okay, these are typical analytical fields. What if I go, for example, over a finite field? I take the field F3, which is Z over 3Z, the field with three elements. And okay, now the nice thing is that I only have a finite number of points because even the plane with these coordinates is finite. You have at most 9 points. And in fact, here the curve, the elliptic curve, is given only by 3 points. The points with coordinate y equal to 0 and coordinate x equal to 0, 1, 2. And so in this case, the elliptic curve is just these 3 points. Welcome to the field of arithmetic geometry, where curves do not seem like a normal curve. So you see, when I actually talk about an elliptic curve, I also need to specify over which field I'm working. Also because, okay, I do not have time, unfortunately, for this, but the fact is that whenever you have a field of characteristic equal to 2 or 3, meaning a field where the multiplication by 2 or the multiplication by 3 actually makes everything equal to 0, then you also have to be careful about the definition of the elliptic curve, because you need not just a thing like that, y squared equal to a cubic polynomial, but you need also some additional terms in y to give the most general definition of elliptic curve. Whenever instead you have a field, for example, of characteristic 0, like R or C, then you can always reduce actually to a thing like this. So in general, when I take field which is not of characteristic 2 or 3, I can always assume that the equation of my elliptic curve is given by a cubic polynomial of this form. Okay, do you have any question about this at the moment?
No, can you just repeat what you said about having finite characteristic and different shape for the equation?
Okay.
So if you have finite characteristic, positive characteristic,
Yes, if I have a
Only 2 and
characteristic, for example, which is 2 and 3, so assume that the field over which I'm working has characteristic 2 or 3, then actually the definition of elliptic curve, the equation that I have to use is something like this. It's y squared plus a1xy plus a2y equal a cubic polynomial in x.
right?
X plus a6. So this is actually the most general definition of elliptic curve. The one that in some sense is the true equation of an elliptic curve. The thing is that in fields which have a characteristic different from these, what you can do, you can complete the square here in y, so that you only have y square here with a change of variables. And then you can complete, you can also, how can I say, complete the cube, so that you can remove the term with x squared. If you are in a field like this, you cannot do this algebraic operation because you cannot divide by 2 or 3. Okay, other questions? Okay, so this was an excursus about the subtle things regarding the definition of an elliptic curve. Now I want to explain why these objects are so important from a geometric point of view. I actually have to say from an algebraic geometric point of view. So second part, geometrical properties of these. So in fact, yes, elliptic curves are, I would say, worshipped by the mathematical community for several reasons, and I want to start with the geometric reasons. The first one, as I already mentioned before during an answer to a question, is that in fact they are curves of genus 1. We can think informally the definition of genus as the number of holes that the curve has when I think about the curve as a two-dimensional surface. And yes, as I told you, the elliptic curve, when I see them as complex curves, they are complex tori. And I think that in fact you can show that all curves of genus 1 are elliptic curves. Yes, it is also true the vice versa. And so you see that in some sense they are the...
In 10 minutes, we have to make a break.
Okay. Yes, in some sense, this is a typical example of why elliptic curves are the most simple, non-trivial object in algebraic geometry. Because, okay, if you take the curve with genus 0, then you can always reduce to the sphere. And this is one of the reasons why elliptic curves are not ellipses, because ellipses, in the end, are surfaces of genus 0. And these are boring, in some sense, too easy to study. Then you have elliptic curves, which are the complex tori. Simple, but not simple enough to be boring. You can do a lot of stuff here. And then you have curves with higher genus. Like, for example, there are the so-called hyperelliptic curves, but you have also other curves, which, okay, they are interesting, but they are, in some sense, more difficult to study because you do not have such remarkable properties as for the elliptic curves. So you see that elliptic curves stand in the middle between easy things and interesting things. And a similar behavior happens if, now let's do it here. I consider another aspect, which is the algebraic aspect, in the sense that elliptic curves are nice because their geometric structure gives an interesting algebraic structure, which arises exactly from the geometric features of the elliptic curve. What do I mean by this? I will explain this by referring to the classical drawing of an elliptic curve, just to explain the group law here. The idea is that elliptic curves have a nice enough equation to define a law of an abelian group, which arises exactly from geometric features. For example, suppose that you want to do the sum of 2 points on the curve, A and B. So I want to find a third point, which I call A plus B. The first step is to take the line between the 2 points A and B, and now I find it here. I find, okay, this is B, this is C. You can always find a third intersection point here when you draw this line, because you have a cubic equation. Just a remark, when I'm doing this, actually I'm doing it in the projective in order to have all the solutions. But you can always find a third point C. Now this C, it's not this one. It's just an intermediate point that I need for my operation. Because the second thing now is to take the line between C and the infinity point of the elliptic curve. This is where the infinity point is really needed, because it is really helpful for the group law, and in fact, it will be the neutral element of this group law. So I draw the line between C and the infinity point, that here I can draw as a vertical line. Again, this line gives a third point of intersection with the curve, and this intersection point will be exactly the point that I was looking for, the sum of these 2 points. Now, this is an intuitive explanation of what is happening, in the sense that when I'm really doing the group law here, when I say draw the line, means that I have to find the equation of the lines joining the points. I have to do the system of this equation with the equation of the elliptic curve, find the coordinates, and so on. But if I do this, then what happens is that my elliptic curve with this operation to my elliptic curve, I call it E. I chose the infinity point. I take this operation, then you can prove that the points of the elliptic curve with this element, base point, and this sum, this is a commutative group. And this is the first algebraic reason for why elliptic curves are so important, because they have this abelian structure of group, which arises from, in some sense, very natural geometric features of the curve, in the sense that this is not an artificial procedure. It's something that really is connected with the nature of the curve. And in fact, okay, I have to mention also that here, when I take the points, if I assume that the 2 points I have chosen have k coordinates, coordinates in a field k, also their sum will have their sum too will have k coordinates, meaning that when I take just the points with k coordinates, I actually obtain a subgroup of this group. And the group of k coordinates, when k is a chosen field, is a very important group, especially for arithmetic applications. I just want to mention also that when you have to prove that this is indeed a group law, you know that you have to verify the several axioms of groups. I think this is the only example in my knowledge where the difficult part of the proof is the associativity law. Because it is very, for example, it is very immediate to verify that this is commutative. And also that the infinity point is the neutral element. The really boring and difficult part that you really takes several pages also of Silverman's book is to verify that this is associative.
Here, when you say line, it's a linear equation.
Yes.
And can you see the commutativity using geometrically? Can you see how y is commutative?
Yes, but because the commutativity is just, you can see already here from the definition, just choosing 2 points, the line is the same.
So it's really the line.
Exactly. And also you can say, because maybe you can think also, what does it mean to sum a point with itself? Just take the tangent in this case. Okay, so let us go on. And now I want to talk about the reason, at least why for me, but also for a lot of people, elliptic curves are important, because they turn out to be very important and in some sense natural objects if you want to study problems related to number theory. I mean, as I was saying before the registration came back, in modern number theory, most of the times you cannot avoid geometry and algebraic geometry. Think, for example, about Pythagoras theorem, in the sense that if you want to find infinitely many integer triples which satisfy Pythagoras equation, so you want to find infinitely many and non-trivial things which satisfy this. When I say non-trivial, also meaning that I do not take multiples of these things. Then, okay, there are many ways to prove this, but an easy way is to use geometry, in the sense that when I start from this equation, actually, if I divide by this, it means that I'm studying what are the points with rational coordinates of the unit circle. And so you have to take to see if this thing contains infinitely many rational points. And it is easy to do this if you use the stereographic projection, because by doing the stereographic projections, you write the equations associated to the stereographic projections, and you can see there exactly a bijection or at least a correspondence between take any rational number here, you get a point with rational coordinates here, and vice versa, if you start from a point with rational coordinates here, you get a rational number. So you see you have infinitely many rational points. And this is an example.
I have a stupid question.
Yes.
I learned about this example from a YouTube video, and I think why don't they teach it more often? This because it's incredibly funny and it's incredibly tricky.
I don't know.
In standard courses.
That's an interesting question, in the sense that
That's an amazing example.
It's really
It's an
easy.
amazing example.
Exactly. There are many easy things that are not explained in basic courses, and I don't know why. I mean, probably you also have to be interested in number theoretic things, in the sense that probably if you're more an analysis guy, you're not really interested into integers that satisfy the Pythagorean triples. But I mean, in a basic geometry course, I would explain this just because it's very quick and gives an insight into arithmetic geometry.
Yeah, I think it also gives an insight on why one should care about rational morphism or something like stuff.
Yeah.
And, it's basically explaining that the stereographic projection, which is straightforward, is a rational morphism, and it has this.
Exactly.
Which is, I think, cool.
And in the end, people sees stereographic projection in topology courses. So this would be just maybe an easy exercise to add for the students to say, hey, with this thing, you can immediately prove this. And you see here the fact that I used the unit circle, so the curve of genus 0. What if instead now I use the curves with genus 1, the elliptic curves? And in fact, this is really fruitful in the sense that a lot of number theoretic problems are used to try to do something like that on elliptic curves, to find rational points on elliptic curves. And I can give some examples. The first example is really basic in the sense that the problem is find all cube integers and rationals such that they are equal to a square, a rational plus 2. Okay, this is not really strange in the sense that this is exactly try to find the rational solution of this, which is exactly try to study this elliptic curve and to find all the integer and rational solution of this equation. Okay, this is not very strange in the sense that the problem is exactly this. There is no strange transformation. I would say that the interesting thing about this problem is that the integer solutions are just finitely many, and in fact, they are just these ones. And proving this actually requires no geometry. You can do this by only using algebraic number theory, standard algebraic number theory, like work with cyclotomic numbers or stuff like that. No, maybe not cyclotomic, just work in this field. If you work in this field, then you can obtain that the integer solutions are just these ones. More interesting is what happens for the rational solutions, in the sense that you can prove, and in order to prove this, you need really the geometry of the elliptic curve, that there are infinitely many such rational solutions, and that if you take the group of solutions with two coordinates, the group is in fact infinite and cyclic. And this is a typical example with elliptic curves of I wanted to study the group of rational solutions. This group is called the Mordell-Weil group, and it's a very central object in the theory of elliptic curves. And in fact, it's the object which is related to the millennium problem, the one about the Birch-Swinnerton-Dyer conjecture. Because what you want to do in this problem is to find the structure of this group for every elliptic curve. Yeah. Then, okay, I can give a second example now of a number theoretic problem, which is related to elliptic curves. And this example is less obvious, I mean, it is less obvious its link with elliptic curves.
This and group structure.
Yeah.
Only smooth case or also for single case.
No, the fact is that the group here, I'm just seeing as an abelian group. Okay, the Mordell-Weil theorem states that this is a finitely generated group. We always know that. So it will be always a finite power of Z times a finite group.
But the elliptic curves are always smooth.
Yes. Yeah, exactly. They are always non-singular over the specific field. Okay, the second example is the problem of rational triangles. Which is take a right triangle with area which is, I can say, a natural number D. The problem is, can you find such a right triangle with sides A and B and C, all rational numbers? Can you construct such a right triangle with this area and sides which are rational numbers? This is an interesting problem which goes back even to Fermat, because Fermat proved that such a triangle exists. If you take, for example, D equal 1, it is very easy to prove it if you take D equal 6, but for generic D, sometimes you can prove that it is not possible, otherwise you can prove it is possible. But the very interesting thing is that, okay, now I do not have the time to explain the steps, but they are not difficult. The idea is that you can construct such a rational triangle if and only if you can find certain solutions of this elliptic curve. Y square equal to x cube minus d square x. And in particular, you can find rational triangles if and only if you can find solutions of these which have y coordinate different from 0. So you do not just need to have a solution, but also a solution like this. And this is also nice from an algebraic point of view, because if I consider the group of Q solutions of my elliptic curve, then by the geometric group law, it is not difficult to prove that a solution of the form x0 is a two-torsion point. Meaning that if I sum this point with itself, I obtain exactly the infinity point. So constructing a rational right triangle is the same as saying that I can find points in my elliptic curve which are not of two torsion. And so again, the geometric problem becomes an algebraic problem over the elliptic curve. And okay, I said a wrong thing about Fermat before, in the sense that when I take D equal 1, it is impossible to construct such a triangle. I confused the things. And in fact, when I take D equal 1, is the one curve I already we already seen during today. And if I look at the Q rational points, the Q rational points of these.
Sorry, I think that the video. Okay.
Okay.
Now
Is
it's good.
it working now?
Yeah. Thanks.
Okay. So I was saying, Fermat actually proved that it is not possible to construct this triangle with D equal 1, because with D equal 1, you have this curve. You take the group of Q rational points of Q solutions, and this group is isomorphic to this. The group of 4 elements, the Klein group, which only has elements of order 2. So this gives the solution for the Fermat case. In my knowledge, there is not a result for generic D. Yes, every point here is a 2 torsion. Okay, so this was the second example that you see. It's not so obvious that you can relate this thing with an elliptic curve. You can do it because the idea is that, for example, if you start from a solution here, then you take something like one side is 2xd over y, and the other one is x squared minus y squared minus d squared over y, something like that. You take the absolute values, and then you can see they verify the relation. But you see, this is not obvious. This is one reason why elliptic curves are interesting. And the third example, which is probably the most famous one that I want to briefly mention, it's Fermat's last theorem. So the statement of Fermat's last theorem is that if I take this equation in integers, has only, okay, here I take 3, but I can take actually any number bigger than 3. So let us write n here with n bigger than 3, has only trivial solutions, meaning that at least one of the solutions must be 0.
There is some question from whom? No?
Okay, so this is the classical statement of Fermat's theorem, and I mean, a first reason why this is interesting is that it's a clearly different behavior from the Pythagorean theorem we have seen before. With n equal to, you get infinitely many solutions very easily. You raise the exponent, and already this is not true. Then we know that Fermat claimed that he had a proof of this, but the margin of its book was not long enough. And I mean, we can almost surely say that he was wrong in the sense that probably he had a proof, but it was a wrong proof in some subtle things, in the sense that probably it was not a stupid thing, but probably it was really subtle in the sense that in 300 years, a lot of people have come with different interesting proofs that became wrong only because of very tiny and subtle things, which in fact originated algebraic number theory. Like we started considering cyclotomic fields because at some point Kummer noticed that when you take the Fermat equation with a prime exponent, you have to consider the p roots of unity, and this for generic prime p deletes the unique factorization.
Yeah, that's another problem. So that I could ask the same question as before. Why don't they teach that much of the Kummer factorization using cyclotomic?
I mean,
more or less
you can see this in any algebraic number theory, in the sense that usually people, when he introduces the cyclotomic thing, mentions this factor. Because in fact, also the fact that you talk about ideals in algebra comes from this, because they started talking about ideal prime numbers, meaning prime elements that behaved exactly like primes in Z, and then Dedekind from that abstracted to the idea of ideal that we use now. And okay, there could be a lot of things that we can say about Fermat's last equation. Also the fact that in fact, people became obsessed with that also because of an economic reason, because Wolfskel in the 19th century, in fact, he did not shoot himself because he really wanted to make it over, but at some point, he started studying Kummer's work, and instead of killing himself, he was so happy with working Kummer's work that decided, okay, I will leave all my money to whoever will be able to resolve this. Wolfskel. He was not a great mathematician, but he was quite rich. So yes, there was also the problem that in the end, the amount of money that he left was completely not valuable when Wise and Taylor solved this, but because of the German inflation between the two wars. But this is another thing. Okay, but I think it was in the end something like probably $100 in the end. Okay, but what is the connection between this equation and elliptic curves? This was the, in some sense, outstanding thing that emerged during the 90s, during the 80s actually, 70s, 80s, because if I remember correctly, okay, this is the thing, was Ray noticed in, I think, was 84 or 85, something like that. It is actually a very recent. The connection with elliptic curves is really recent. Yes, in the sense that he noticed that assume that you have a solution. So assume that A, B, C is a non-trivial solution. Consider then this elliptic curve. Okay, you can always reduce to exponent which is a prime p, because if you can prove the theorem for prime exponent, then you immediately have it also for general exponent. This is easy to verify. So assuming you have a non-trivial solution, then you can construct this elliptic curve, and then this is indeed very technical and very difficult, but what happens is that okay, I call this curve E.
And the fact that you can generalize this thing over any integer. Like if you prove a prime, then you can also take
Yes.
and requires factorization.
I mean, it's just that yes, if you take n, which is p times q, then if you have a solution A, B, C, for example, for p, you just need to take yeah, yes.
It's not already anything. Okay. Yeah. Then
Yes, yes, I'm just considering the normal integers. Yes. Yes, you just have to take from a solution, you get immediately another solution, which is solution elevated to a certain exponent, just to match the things. What do you want to have? You want to have p in the end because you want to reduce to the p1. So what you want to do, yes, stuff like that. Okay. Okay, I was saying that if I take this elliptic curve, assuming that this is a non-trivial solution, then what happens is that for some technical reasons, which are very difficult to explain, then this curve E would be an elliptic curve defined over the field of rational numbers, which is not modular. What does modular mean? This is a technical thing in the sense that there was this conjecture by Taniyama and Shimura I think it's from the 50s or 60s, which states that every elliptic curve over the rational numbers is associated to an object which is called a modular form. This is the meaning. I mean, there is a precise meaning of that, very technical, but the idea is that every elliptic curve is associated to something that is called a modular form. This is called being modular for an elliptic curve. And people wanted to prove this, and Frey noticed that if a non-trivial solution of Fermat exists, then the arising elliptic curve would be an example of of elliptic curve which is not modular. And what Wise with this is the help from Taylor did was to prove that in fact Taniyama Shimura, it's true not in general, in the sense that they did not prove this in general, but for the elliptic curves also of related to Fermat problem. In the sense that they proved that a class of elliptic curves, which are called semi-stable elliptic curves, are modular, and the fact that semi-stable elliptic curves are modular force, in fact, this curve, exactly this one, to be modular, which is a contradiction then with the fact that we have a non-trivial solution of this. Here I mention the contribution by Taylor because Wise did a really an amazing job, something very titanical, incredible. But the fact is that the first proof he gave was not complete. He noticed this thing only after he presented it in a seminar. And he spent, I think, another year just trying to fix that. And he did it, but he did it also with help from Taylor. So Wise, yes, I think he did 90% of the work. So, and he deserves all the critical acclaim he gets. But the contribution from Taylor is really, really important, at least for this problem. And I also want to say that now the Taniyama Shimura is known to be true. In fact, a few years later, after from this result, I think this is from 93, 94. In 2000, 2001, a lot of people, including, I think, again, Taylor, proved that Taniyama Shimura is true. Okay, so this is the important reason why elliptic curves are related to the Fermat problem. And the study of this connection, in fact, originated a lot of interesting but very difficult mathematics with a lot of concepts, a lot of tools. And now what people are trying to do is, for example, because here we just take Q, but nobody forbids you to take here, for example, Q of square root of 2, Q of I, other number fields. And people, again, are trying to say, can I obtain a Taniyama Shimura over these different fields? And a lot of great mathematicians of today, like Anna Karagiani, Jakob Zimmerman, a lot of people are working on this. I think they are proved now that maybe all real quadratic fields satisfy Taniyama Shimura, something like that. Probably also imaginary quadratic fields. And they're trying to work with other fields. Okay, and now in these last few minutes, I think it will take at most 5 or 10 minutes, because I just wanted to briefly explain 2 reasons why elliptic curves are important, not only for abstract number theory, but also for computational number theory and cryptography. I will be quick with this, but this is important. I would say just 2 things. The first one is that, okay, you know I mean, the most difficult problem in computational number theory in the end is always the factorization of the integers. In the sense that you can think of a lot of results in number theory, but not only number theory, which are very easy and very elegant, but there is always one caveat that is you need before to compute the factorization of an integer number. And this is a painful task. I want to mention that, okay, there are nowadays a lot of different algorithms for computation of the factorization of an integer. One very interesting algorithm was developed by one of the Lenstra brothers in, I think, the 80s. And I think he was Hendrik Lenstra, yes, one of the Lenstra brothers. He gave a probabilistic algorithm to compute the factorization of an integer, which uses elliptic curves. The idea is that if you want to factorize an integer, then you choose an elliptic curve which you associate to this integer in a certain way. And by using the computer, you start to sum points of this elliptic curve and try, whenever at some point it happens that during the sum there is something wrong, then this something wrong is with high probability related to a factor of the integer. And so you find a factor. This is not deterministic in the sense that there is no proof actually that what you get is always the factorization of the number, but the probability that the factorization is true is computed and is really high. And in practice, it seems that these have never failed. And I think, in fact, most of these things of factorization now are dealt with probabilistic algorithms because deterministic ones take too much time to give an acceptable result. You just need to assure that your probabilistic algorithm is strong enough to give a confident result. So not something that gives you the correct result in 50% of cases, but something much, much stronger. And the second application is okay, you probably heard about public key systems, like the most famous one is the so-called RSA, public key system in cryptography, from, this is Adelman, this is Shamir, I think, and this is Rivest. Just remember Adelman, I don't remember if I said the names correctly. That in fact, they obtained an interesting and very strong cryptographical system, which is based upon the fact that, as I told you before, it is very difficult to factorize a large integer, even if you know that it is the product of two primes. It is very easy to go this way. If you have the two primes, just multiply. It is very difficult to go this way. If you have the number, try to factorize it. And why this is called a public key? Because in this cryptographic system, this is public, this is known. Everybody doing working in the system, exchanging the messages in the system, knows this number. But the two primes here are secret. You can recodify your message only if you have, I think it just needs, yes, one of the primes is needed, but you need to have at least one of the primes. This is a very successful cryptographical system, but it is also a very heavy cryptographical system. When I say heavy, I mean from a computational point of view, also in the size of the messages that you have to send. And what several people did, I think at the end of the 90s, and probably also involving people like Koblitz, so very big names of elliptic curves, was to define a public key system with elliptic curves. So instead of just using an integer and looking for its factorization, the problem now is you have these public elements, which are a finite field, FQ, an elliptic curve over the finite field. So this is a finite number of points, but Q may be big, so this may be a big number of points. And a point on the curve. These are the public data. What are the secret ones? The idea is that now the secret is that you have Alice and Bob, as always in cryptography, that want to send messages. They share this common knowledge. What they do, they try, for example, Alice will choose an integer m and will sum p m times with itself and will send this to Bob. Then Bob will try to do the same thing with another integer. Let us call this q. N times q will do a similar thing and send it back. And the fact is that using the properties of the group law of an elliptic curve, by doing so, they can recover the original point by just knowing the original data. There are actually many other details that I would have to say to explain in detail what happens here, but in some sense, it's the same thing as here, in the sense that you are starting from something which is known, but everyone manipulates it in a private way, and you who have the secret keys can go back to the original point because you have the secret keys, and the secret keys exploit the group structure here. And why was this important in the end? Because, okay, it works and it's safe just as RSA. But the most important thing was that it's lighter, in the sense that it takes less operations, and the messages it sends are, I think, 5 to 10 times lighter than the messages sent with this system. And in fact, I think this was developed especially thinking about mobile phones, cryptography for mobile phones, because you needed a system not heavy as the one for the computers.
Where do you input the data? Is it the password of the data?
I mean, yeah, the data is like, yeah, this one, in the sense that you start from the public thing and then you choose an integer, which can be a number. I mean, whenever you insert a thing like a password or a message, it gets converted to a number, and you use this number to do this sum.
It's like you can also send text messages.
Yes, exactly. The idea is exactly that you convert a text message or an order or something like that in a number, and then you use this number to do the operations. Okay, so this was a brief excursus about over the main features of elliptic curves. I think most of the times, I think in the next lessons, most of these features will be developed more in detail. And I think the next one is up to Martina, if I'm not wrong. So in the next lessons, we will be seeing more about the geometric features of the elliptic curves, and then more about the arithmetic features of the elliptic curves. And I think that for today, we can stop here. Thank you very much.